today we're mainly going to talk about binary digital Boolean logic, binary numbers, and the combinational logic. So this is as a review course, a review lecture that help you to understand the very basic things about computer architecture. Then when we talk about Boolean logic, binary numbers, and combinational logic, especially combinational logic, is the part that if you design circuit on your own, very low level design, that is something really important that you really have to know. Then, but as a computer architecture researcher, if you want to research something at a higher level, you probably do not need to know things at this level. Then you only need to, like, say, when you need a cache, okay, you need a cache, just imagine as if it's a software, but executed, the algorithm is executed in hardware, then that's good enough for computer architecture design. But I want you to say, I want you to avoid a feeling that, say, when I design something really advanced, like a CPU core, a GPU core, or a cache unit, that you feel so missing that how these things are implemented internally at the low level, right? So that's why I want to introduce this topic at the very beginning. The key idea is eventually, oh, if I want to implement something that is complex, I know, oh, this is possible. If I spend a lot of time, probably a few months to years with low-level design, then I can make it. Or if I have a team of people who work for a month, they can probably help me design these type of things. That just want you to know that things are possible, okay? So starting with Boolean logic, then what is Boolean logic? You probably write code on your own that's true and false, right? Or in circuit, we just call it 0 and 1. So there is either true or false, 0 or 1 that are logic values, right? Then high and low are voltages. Now we typically use high voltage to represent 1 and low voltage to represent 0. Now why we use Boolean values is because we want to increase this reliability. That you need to consider, although we consider digital logic always works in 0 and 1, high voltage and low voltage. Internally, every digital circuits are actually analog circuits. So when we say analog circuits, it has no 0 and 1. It's always a continuous voltage or current, right? But if you consider these things are analog circuit, then you need to consider, oh, sometimes if we consider 5 volt is the highest voltage, then my value may not be as high as 5 volt. It may be 3.3 volt. And do I consider it as a 1 or 0, right? If I simply set a threshold, it's the most reliable way. Then, of course, you can design things that, design a computer that works in not a Boolean design. You can have 0, 1, 2, 3 numbers. Then to set, say, 0 to 1 volt is 0, then 1 to 2 volt is 1, and above 2 volt is 2. That works, and there are even some prototype of hardware is designed in that way. It's just not that simple, not that easy, and the transistor has this strong, like, shut down and close effect that makes this 0 and 1 design really simple. That you simply use 0 and 1 to control if a transistor is connected or not. Okay, so I don't know if anyone has watched this video before. And you should try to watch this video. This is a very educational video, and this is a very very important research direction in the computer architecture domain. Is generally typically called reliability. No computer is safe because those things that keeps the high voltage and the low voltage, especially keep the transistor shut or connected, is only a few electrons, right? It's only a few atoms. But there's high energy rays from the universe that may hit your computer, that may hit your CPU or GPUs in your computer. Then it may flip a bit, then cause some data to be wrong. So this is a real consideration. Now, if you have multiple values more than 0 and 1, it's more likely to make the flip. Okay, now later on we can try to discuss some of the effect of how we can prevent this type of reliability problems. But here we're talking about logic operations, and you should be very comfortable with these type of things. Now we only have 3 basic logic operations: not, and or. We list the possible values with the truth table. So on the left side is the input, and on the right side of this vertical bar is the output. So if we have 0, then output is 1. If I have 1, the output is 0 for not operation. Then and means if both of them are true, then our output is true. For all, if any of them is 1, then the output is 1. Okay. Then, so by the way, we use this type of representations as a prime sign as not, and xy as and. So if you consider anything multiplied 0 is 0, right? Just an easy way to help you understand. Now we use a plus sign. There's a little problem that 1 plus 1 is still 1, but it's just you need to know this is Boolean logic. Okay. Now we also have one extra operation that is called XOR. So it's defined in this way. Okay, it's if they're different, they're 1. If they're the same, they're 0. Okay, then actually XOR can be represented with and, or, and not representation. So sometimes you want to use XOR, sometimes you can just use very simple representations. There are different representations. Then with logic representation, Java or Java bitwise operation or circuit operation. Now here we're using this set of representations. There are some very simple rules. I don't want to teach you to do the calculation. Then if there are some really hard problem, it's gonna take some time for you to solve those problems. But those are not the most important part of this course. But let's read these rules together. Identity, that means 1 or x is still x, x and 0 is still x. Okay, then complementary is x or x and x prime is 0. X or x prime is 1, right? Either their itself or the reverse must be true. So because they're opposite. Then they can swap. Then they can apply this type of rules. And associative, they can also apply this type of rules. Then it's basically the same rule as multiplication and sum operations. Then there are more rules. Then if we consider 0, then the opposite side of 0 is 1. Then x prime prime is x itself. And this is the other way compared to identity absorption. Then this is, I think these two rules are slightly more advanced and useful. That means if x is already there, x plus y, this is x or y, then x and x or y is still x. This y is not useful. This is a little bit hard to think if I only give you a few seconds time. Then at this stage, don't think too much about this. Then if you want to verify this, the easiest way is just to list the truth table. There's only 4 possible inputs. Then calculate them. Then you can see on this side is always the same as this side. Okay. Then De Morgan's law, that means x or y prime is equivalent to x prime, and x and y prime equals x prime or y prime, right? Then De Morgan's law is something that I really use in writing a program. Sometimes I write an if statement. The condition is a little bit complex. The condition is something like this. Now I may feel represented in this way is easier. Then I may just change it to this style. Okay, so it's slightly useful in writing program. I just want you to know, okay, there are some rules that you can do the calculation. We can mathematically prove them, or we can just list the truth table and to compare this side. They're always equivalent. Okay, so later on we will see different type of gates. There are AND gates or gates can implement this type of logic and can perform complex calculations. But before we go there, let's consider how we can make the binary really useful, how this binary can represent more complex things. Okay, so when we talk about integer, we want to use binary to represent integers. So that's a base 2 number. Right? I think you probably all have learned how to convert a base 10 number to a base 2 number. Right? So base 10 number can be represented in this way. It's the digit 5 multiplied by 10 to the power of 0. That's 1, then that's 10, that's 100, that's 1000. That's how the internal meaning of this number. Now, if we consider a binary number, it's basically the same thing. Then base is represented here, right? So base 10 is use the 10 as the power base, and here use number 2 as the power base. So this number represents 1, 1, 0, and 1. Okay, 1 multiplied 2 to the power 0 because it has a weight of 1. It has a weight of 2, has a weight of 4, has a weight of 8. And just sum them together. If you do this calculation, you can easily convert something to convert this thing to a base 10 number. So if I quickly ask you to convert 1101 to a base 10 number, what would you do?
It would be I'm sorry. You would basically just go through this, and then you get the answer in decimal. So that would be 13.
Yeah. So you can calculate this, right? That's a little bit more formal way. Then sometimes I'm too lazy to do this. I just count from 0, or count from somewhere I know. For example, I know 1111 is F. 1000 is 8, right? I just start to count from there. That's probably, if it's not too long, then it can happen. So how I count is 0, 1, 1, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, then 1, 0, 0, 0. And don't read it as 1000, just read it as 1, 0, 0, 0. Okay, then one quick operation is shift. Then this shift is very important operation that we'll learn in computer architecture. Almost every computer architecture support this shift operation. Then for shift, then if we shift the digit to the left by 1 in base 10, we basically multiply this number by 10 because we add a 0 there. Now if we shift the left in binary number, in base 2 number, we still add a 0. Then this means we multiply by number by 2. Okay, so left shift is multiplied by the base, and the right shift is divided by the base. Okay, so we want to do calculation. In base 10, we do calculation, right? Then in base 2, we also do calculation. How we can do calculation? The rule is roughly the same. If we do this, it's 6 plus 5 equals 11, then we put a dot or plus, put a 1 there. Now 1, 4, 6 is 1. So here we basically follow the same rule. 0 plus 0 is still 0. This is real plus. Okay, this is not the OR operation. 0 plus 0 is 0. 1 plus 1 is 0, and put 1 here, right? Now 1, 0, 1 is 0, and put 1 here. 1, 1, 1 is a 1, then put an extra 1 there. Okay, so if we do this type of operation, it's equivalent to doing the same operation in base 10. It gets, so if we get this, the value of this number, the value of this number, the value of this number in base 10, they are the same. Okay, so the sum, the add operation, multiplication operation, division operation, they are the same in different bases. It won't change. That makes the digital design that is two-based in a two-based system possible. Okay, later on we're going to see how we can design an adder in binary. Adder in binary is basically we first add this number, but we also need to consider a carry. So we are basically adding 3 digits together. So if we know the rule of if we know the rule of how to do the sum operation of two digits, then if we can write the possibility, all the possibilities, and do the calculation, and we can calculate for this input we can get this output, for this input we can get that output. Then if we can list all the possibilities, then we can express them in a combinational logic. We can calculate them in a with circuit. And then you also, as a computer science student, you should also quickly know these hex number conversions. So from decimal to binary, octal, and the hex number are just, you can use this table to make the conversion, or you can just count. So from binary to octal and to hex number conversion is actually very easy. Then from binary to octal, you just simply combine 3 digits. Then you can put 1 digit there. For hex number, you can just put 4 digits, and it makes one number, 1 digit there in the hex representation. So when we write down a number like f, why we want to write 4f there rather than 0 and 1, a lot of 1, it's just much easier to write. Right? I don't want to spend this long piece of paper. So writing in hex is a much more concise number. So when you see hex number, you should need to have a feeling about what's the value of this number in decimal and in binary. And bit and byte are typical units that we're going to use. Then just consider 1 bit is a very small thing, then 1 byte is a byte. Just consider you bite something, you bite a piece of food, right? In early days, bit and byte conversion is not necessarily 8 bit per byte. So in early systems, it can be 4 or 5 or something. And later on, it just converged that everyone use 8 bit. Then this is a very important topic about data range. So if you use 1 bit, you can only represent 0 and 1, right? And if you use 2 bit, you can represent 4 numbers. That's 0, 1, 2, 3. Now if you use 1 byte, that's 8 numbers. Then you can represent number 0 to 255. And 4 bytes is this amount, 4 million something. Then this is not actually a very big number if you consider the number of bytes in your system. Now remember, early days we use 32-bit system, right? So what does 32-bit system means is a 32-bit system basically use 32-bit number to represent an address. An address is a byte in your memory. Okay, it's a byte in your memory. So you can have at most this number of bytes in your memory. So what's the value here? The value, it's only 4 gigabytes, right? Everyone, pretty much even my phone has more than 4 gigabytes of memory. So if we're using 32-bit machine, then we're limited to 4 gigabytes of memory. That's why pretty much all the machines, even phones, are migrated from 32-bit to 64-bit machine. Then just consider 32-bit, right? If we add 1 extra bit, that becomes 8 gigabytes. Then 2 extra bytes, that becomes 16 gigabytes. So 64 gigabytes is almost unlimited space at the standard of right now. Now maybe 10 years later, that's also too limited. We're moving to 128-bit system. Okay, let's talk about how negative numbers are represented. Then negative numbers, the simplest method is in this way. We can dedicate 1 bit, the first bit, to represent the sign. So if it's 0, we just say it's a positive number. Then it's a 1, then we say it's a negative number. This is method 1. And so what's the problem with this design? The problem is we're duplicating 0, right? For 0, we have a positive 0 and a negative 0. We have 2 different ways to represent 0. And also, if we want to sum these 2 numbers together, we need a separate type of logic, like a combinational logic. different set of circuit to calculate. We need a method to calculate positive and positive, negative and negative, and positive and negative. We need 3 different set of ways to calculate these numbers. So this is really annoying, and that's why we want to avoid this number. So the second way is we can flip out a bit, and this method is called one's complement. Then it's not really useful, but it's just an intermediate step, right? So we can first flip this representation. Then we say, okay, this is a negative number. And we can still use the first bit to tell if it's positive or negative. Okay, still it won't solve the problem that we cannot use the same digital circuit to calculate positive number and the negative number, the sum operation between a positive number and a calculated number. So we add this minor tweak to flip out a bit and add 1. This is very counterintuitive at the beginning, that's how it works, but I can tell you that this is how we represent the negative 82. You just assume this is positive 82. Don't need to verify this, but if we flip all the bit, you can see the last bit is the last 4 digits should be 1101, right? Then we add 1, then becomes 1110. That's something we call 2's complement representation. Then, so what's the advantage of 2's complement representation? Just use one example. How we represent 0? We represent 0 without 0. That's simple, right? So how we represent 1? Nothing changed. How we represent negative 1? We just use all 1 to represent negative 1. Just consider we're converting this to 11111110, right? Flip out a bit and plus 1. 11111110. Then this 0, by adding 1, the last 0 becomes 1. So then we get all 1s. Just think about this. If 0 minus 1, right? What will happen is something that we call a natural overflow, right? So just imagine we have a 1 there. Now if we have an imaginary 1 in front of it, and we reduce by 1, it becomes 0, 1, 1, 1, 1, 1, 1, 1, 1, right? Then we remove the imaginary 1 in front of it, we get all 1 there. The logic still holds. Just one set of logic, that one set of circuit that guaranteed to work for both positive number and negative numbers. Okay, that's how 2's complementary works. Okay? Just consider, like whenever I think about this, I just feel the early computer design, they're just too short of devices. They want to reduce the number of gates. They don't want to develop a new set of numbering system. They don't want to design a new type of like operator, like the circuit that's for positive and negative number calculation. So they tweak the numbering system a lot so that it works like perfectly for both positive numbers and negative numbers. Okay, always use these a few special numbers to help me remember how this 2's complementary system works. Okay, we're talking about numbers. By the way, if I have 1 byte to represent negative numbers, what are my range? What's the smallest number that I can represent? And what's the largest number I can represent?
The largest number to represent would basically be the largest possible unsigned number you can represent divided by 2, and then the smallest one with the same thing, except one of those is minus 1.
So just use binary. What is the largest number? in binary that we can represent? 127, right? So 0, 1, 1, 1, 1, 1, 1, 1. So 127, right? Now what's the smallest number that we can represent? It's basically 1, 0, 0, 0, 0, 0, 0, 0. That's negative 128. Okay, just consider, if we consider 0 as positive number, it's half and half. Okay, negative 128 to positive 127. So remember, there's always a feeling of encoding. What is encoding? Your computer always just work in binary. It doesn't really know what the meaning of this number. It doesn't really know it's a signed number or unsigned number. If we have an unsigned number, the highest value we can represent is this way. It's 255, right? So 255 can be both negative 1 or can be 8 ones can be both negative 1 or 255, depending on how you define this number. Okay, so we're using two different encoding methods to encode the same list of binaries. Okay, there's always a way, like the encoding meaning of these binaries. Your hardware, your memory is just a huge list of 4 gigabytes, 4 giga multiplied by 8, that number of 0 and 1s. Now, how you use those numbers, it depends on your program, how you treat those numbers. So how we can represent the floating point number? That means that's not an integer, like 5.5. How we can represent it? Then according to IEEE 754 standard, this is how we represent it. We just encode it in a more complex way. So by the way, this is how what we call a single precision. A single precision basically uses 32-bit to represent one floating point number. Okay, I'm just going to use an example to tell you how it works. Let's say 5.75. Okay, how is negative 5.75 works? Let's do it step by step. Now we can convert this to a binary number. We didn't talk about the decimal part. It's basically this 1 is 0.5. This 1 is 0.25. Right? Just consider 2 to the power of negative 1 and 2 to the power of negative 2. Right? So that's where this 75 comes from. Then we normalize it. What does it mean by normalize is, remember, you probably have learned scientific representation, right? When you use scientific representation, you only want to have one digit right before the dot, right? You only want to have one digit right before the dot. And here in scientific representation, you use 10 to the power of 2 or 10 to the power of something. But in scientific representation of binary, we use 2 to the power of something. So this is how we normalize this number. Consider the sign, we have a 1, right? So we can already define this sign bit is 1. Now, exponent is this number is 2, right? So here, this exponent, we just write 2 there, or 1, or 1, 0, right? Then here is the exponent with bias. Okay, so this is how it represents both a positive number and a negative number. We actually store 129 there. So just consider, if we store a negative number there, then plus 127, then it becomes a positive number. So it's just another way to represent positive and negative numbers. So here, what we're recording is 1, 0, 0, 0, 0, and 1. And the mantissa is the real value of this number. So we keep it 0, 1, 1, 1, 1, 0, 1, 1, 1. There's an actual 1 there. So we do not represent the first one in front of the decimal point. because we know there must be a 1 before the decimal point. We just skip that one, right? So this is eventually how we represent the floating point number. Okay, it requires a complex conversion. Okay. So basically, we can roughly estimate what's the range of numbers that we can represent, right? So what's the range of number we can represent? If this exponent field, that we can go with negative 127 or positive 128. We don't need to consider the boundary case. Just negative 127 to positive 127. That's a 2 to the power of 256. That's the range of number that we can represent, right? Now, 2 to the power of 127 is actually a very, very large number. So the quick question is, if we use 8 byte to represent integers versus use 8 byte to represent floating point numbers, which one can represent more numbers?
Technically the same amount of numbers, but one of them will have a larger range if it is in decimal.
Yeah, that's a very good answer. So the quick answer is they can represent the same number of numbers. The total possible numbers to be represented by 32-bit is only 2 to the power of 32. It's just a matter of encoding. Because we have the exponent value so large, if we have that large value, and it's 2 to the power of 127, in theory, we should have 127 digits in the mantissa part to fully represent that number, to have a full precision, right? But that's impossible. We only have this part. So if you represent a large number, super large number, we're somehow sacrificing some accuracy there, right? But we think this is typically good enough for representing or normal cases, or to describe our real world. So there's a big problem with floating numbers. What's the problem with floating number? 12 divided by 4, what do we get? We don't exactly know, actually. We can get 3.0, or we can get 2,999999999, right? Now, if we take a floor operation, it can either be 3 or 2. Just hard to say. Okay, so this is a big problem with floating point numbers, with single precision floating point numbers. So if you need more precision, you can go with double precision. And double precision is basically using 64-bit values to represent a floating point number. Then you can describe with much higher precision, now with even higher range. However, more likely, these days, people do not care about that precision, especially when machine learning workloads are there. And people more care about the calculation capability, right? Because the more bits you have, the harder the calculation is. The fewer the bit you have, the more likely that you can have the calculation. I'm just comparing this. It's pretty much the state of art NVIDIA GPUs, right? Let's look at this NVLink version. For 64, floating point 64, it can support 30 teraflops. So by the way, what is teraflops? What does flops represent? Okay, so if you're, so if you work on computing, trying to estimate the computing power, flops is probably the most important values that you need to consider. By the way, this is a screenshot I take. I don't exactly remember where I take this screenshot. They just mix the use of this lowercase and higher uppercase s So typically we consider lowercase s and uppercase s means different things. So FL means floating point. Okay, OP means operation. So floating point operation lowercase s is a plural form of flops. Okay, I think it's a mistake. Okay, but I'm just telling you this. Uppercase S is floating point. O represents operation, P represents per, S represents per second. So this represents, capital S represents how fast or the capability of a device. Lowercase s typically represent the workload that is required to be done. Okay, but anyway, just consider these are uppercase s. If you look at FP64 and XP32, it typically doubles, right? If you consider there's no FP16, right? We can only compare this tensor cores. Now FP64 tensor core is 60. Then FP32 is much harder, much higher. Then FP16 tensor core is about twice the value. FP8 is again twice the value of FP16. Okay, this is how these things are, how these systems are typically configured in GPUs. So the lower, as we go with half the length of this floating point number, we double the calculation capability. So even some GPUs, especially today, if you buy gaming GPU, a graphics GPU, they very likely they do not equip the capability of calculating FP64 numbers. They think it's not useful. We don't really need that precise because eventually you need rendering, right? Like how precise your color, probably you won't tell the difference if you are really using FP64. Okay, so FP16, there are different. How is the way that we represent it? It's basically 1, 5, 10. The bit sign is always there. We cannot really ignore the sign bit, right? Then the exponent is 5. It's still, we can represent a reasonable range of numbers. Then the mantissa is much smaller because we don't care about the precision that much. Now it's widely used in deep learning, especially a few years ago. If you consider LM, we're starting to use FP8, or some people even using FP4. There are two different ways to represent FP8. It's 1, 5, 2, have more range, but very low precision. Then if you consider 2, that's basically only 2 bits, the 4 possible values, 0, 0, 0, 1, 1, 0, and 1, 1. So basically that represents 0.25, 0.5, 0.75. That's pretty much the only value that I can represent, right? Then with 143, we have smaller range, but slightly higher precisions to represent. Then, so floating point representation, so other than floating point, when we say floating point, is the point can float, can move everywhere because we use an exponent field to represent the scale of this number. But sometimes if we know the range that we're going to use, for example, in machine learning system, if I know we're only going to use +2 to -2, and we're not going to use huge ranges, we can simply use fixed point representation. What is fixed point representation? It's just another way to encode these 0 and 1s. So, for example, we can always just represent an integer, and we externally define the scaling factor. Right? For example, our scaling factor is 1/100. That means if we store 50, then we always get number 0.5. Okay, it's a much easier way to represent floating point decimal numbers. So this type of system is used in something like neural engines that can calculate machine learning workloads. Or we can use this integer part to represent the integer for integer part and the integer for fraction part. Here, for example, we can use 6-bit to represent the integer part and another 10-bit to represent the fraction part. And you can see here, as in this representation, using a fixed point number is not very different from the floating point number, but we can reduce the number of bits that we use to represent these numbers. And in terms of area and the power that is used to calculate these values, then area is much smaller and power is also much smaller, right? When we extremely care about performance, but we can sacrifice some performance, yes, we can go with a different type of number representation, different encoding. Okay, so this comes to a fundamental problem then in computer architecture. In computer architecture, there's no best way to solve a problem. You need to find, say, oh, I find a particular problem. I really want to optimize from my problem. Then you observe the characteristics, the uniqueness of your problem, then find a solution to solve your problem. Okay, so in terms of machine learning, or at least the type of machine learning algorithm, their uniqueness is their range of this number are relatively fixed. Okay, then that's why they can use fixed point representation to represent these numbers. Okay. Any questions so far? So quickly go through a few other type of values. That for strings, you probably know this ASCII representation, right? For every letter or every symbol, like M, we use number 77 to represent it. So this is a predefined encoding. Then it's a consensus of the whole human world to say which number represents to which symbol. Then ASCII can only use 128 numbers, so it's only 7-bit. But basically, these are only English letters. Now, if you represent something like Italian or Spanish word, then there's some special symbols you just have no way to represent, or other like Chinese or Korean or Japanese character set, then ASCII is not sufficient. Then they define this thing called Unicode. Unicode is it's not an encoding, it's basically a character set. So which character that we need to represent. Now it has a number, but this number is not necessarily the encoding that we use in memory. What is encoding? A more common encoding is UTF-8. Now UTF-8 can use either 1 byte, 2 bytes, 3 bytes, or 4 bytes to represent a character. So a quick question. How can it support both 1 byte and 2 byte and 3 byte and 4 byte?
One of the later bits is an indicator that there's more bytes.
Yeah, it's a very common way for compression. That, for example, here, so the first byte is always ASCII code, but there's a reserved bit, right? Remember, we say ASCII is 7-bit. Then there's a 1 reserved bit. If that bit is 1, then that means, oh, 1 byte is not enough. We use an extra byte to encode it. And there's also reserved bit in the 2nd byte. There's always reserved bit in the 3rd byte, so that we know how many bytes are there in a character. Right? Up to 4 bytes, that actually can represent a lot of characters. And also, it's rather compact, that the file size is not super large. Then you can avoid, say, if only write in English, 1 byte is good enough to represent 1 character, then our file size is not super large. Question?
Fit into something like UTF-16 or like Wi-Fi in Windows-based.
So I would say it's just encoding. It's just different encoding.
So it took them a while to figure this out. And so the first thing they tried to do is just take the ASCII and add another byte. That's where you get 16. And so they just said, we'll just make a 2-byte character. And and that's what Windows wins. Later on, they figured this out and said, let's make it smart, dynamic, changing encoding, and that's where this came from. So that was an earlier version.
So, so UTF-32 is our UTF-16. My understanding is it's more efficient for Chinese or for Japanese numbers, because if you encode in UTF-8, it requires 3 bytes, but in UTF-16 you only require 2 bytes. But 2 bytes is kind of limited. But UTF-32 is less efficient. Still, UTF-8 is the most is still the most common encoding method that we use today. Okay, so for strings, another thing you need to consider is termination. We can either use 0 to represent the termination, or we can use length-based. In C, we use 0, then it creates lots of pain for us. Now, if we have a length-based, basically have another integer to the first integer to represent the length of this string, then it's just more flexible. Now, for images, we know we have pixels and brightness, right? And for brightness, we can either represent with an integer number from 0 to 255, or we can use a floating point number from 0 to 1. Now, in machine learning, definitely it's more common to use 0 and 1, but for more efficient storage, we are more likely to use an integer from 0 to 255. Now, we have different ways to store these values, especially we consider channels, and channels are different colors. Now, for human eyes, we can only see red, green, and blue. So we can have different channels, and there's different channel order. So for example, we have N is the pictures, different pictures. C is the channel, HW, right? So if we have NCHW, then we store in this way: 0.3, 0.3, 0.4, no, 0.1, 0.2, 0.3. But no, I need to consider a second row. 0.3, 0.3, 0.4, 0.3, 0.4, 0.5. We store in this way, then go to the next channel. Right, this channel, if they're closer to the left side, they're outer loops. Now, if in this way, NHWC, we store in 0.3, 0.1, 0.3. Okay, so in machine learning, especially in GPU architecture, you will eventually see they can cause very different performance just by encoding these pictures in different ways. Then for vectorize the image, there's no pixels, but we use these symbols to represent. They're basically coordinates. Say move to a certain number, which is A, I don't really remember. Then H is a horizontal line, so it's another way to represent images. Then for audio, now we basically quantize every sample, right? Now we use different number of bits to represent how strong a signal is at this point. So the key point until this point is pretty much everything that in our world can be represented by digital values by pure binary numbers. Now, if we know how to convert a binary number to another binary number, then we can design circuits to process things and to automate things. That's how computer was designed at the very root level. So that comes combinational logic. Last year, I spent 2 lectures to talk about the whole thing. And this time, I try to spend 1 or 1.5. Okay, so combinational logic is a type of circuit that we can design if we know everything can be decided ahead of time. That means if we can write a truth table, no matter how long it is, if it's a very long, it's still okay. But if we can define everything in the truth table, we say we write all the combinations for the input values, then we can manually calculate the output. Now, if we can produce those tables, then we can define this logic in combinational logic. Now, later on, we're going to talk about sequential logic. The difference between combinational logic and sequential logic is combinational logic can calculate the result immediately. Sequential logic needs some time to calculate. So what's a combinational logic? So it's a digital it's a digital circuit. And for digital circuit, that means we only consider 0 and 1s and different type of gates. Okay, the output depends only on input, and we can say correctly working combinational logic, the result is deterministic. Okay, if it's not deterministic, there's likely something wrong with it. Then there's no memory and there's no feedback. No memory, there's no feedback. That means the result will not be stored somewhere to go back to the combinational logic in the next cycle. We only have a fixed number of input and fixed number of output, and it never goes back. The instantaneous response, that means we consider it takes no time, or at least at the architecture level, we consider there's no time. But it's something very practical concern that your combinational logic must calculate the result within these cycles. You probably heard that our CPU runs in 1 gigahertz, 2 gigahertz, right? So 1 gigahertz that means 1 nanosecond, right? 1 nanosecond is a cycle. So our whole thing has to finish in 1 nanosecond. Then, but can this finish in 1 nanosecond level? This is something to be considered at the electrical engineering or digital design domain. It's not necessarily something that we really have to consider in the computer architecture domain. As long as you have something in mind that you cannot do too many things in one cycle, that's good enough. Okay, then it implements Boolean expressions. If we can write down something into a Boolean expression, using the AND, NOT, and OR operators, and if we can represent it in a Boolean expression, then we can implement in a combinational logic. So we start with gates, then there's gates representations. Then let's start with the simple one. AND gate is a round, it's round in the front. Then OR gate is there's an angle in the front, right? So NOT gate, the three most important gate is AND, OR, and NOT. So NOT has a circle there. Then the triangle means basically we don't do anything. There's a buffer here. Buffer basically means X is still X. Now why this part is necessary? It's just some delay. So if we have one path that has a lot of gate, then another path has no gate, then we probably add some buffers to intentionally delay it. But still, in computer architecture, we do not really consider this super low level, like picosecond level differences. You can basically ignore buffer there. Then you see there's a small circle that means NOT. So NAND means we first do an AND operation, then the result we take a NOT operation. Okay. And for OR, NOR is the same thing. We first calculate an OR operation, then then flip the result. XOR, we have talked about that before. It's represented in the extra line behind the OR gate. Then XOR, XNOR. It's not, then flip the result of an XOR gate. Okay, so when we draw circuit, we're more likely to draw AND or NOT gate, or sometimes NOT gate can be simplified as a circle. Sometimes we can even draw something that we put a circle here to instead of a NOT gate. Okay, we just put a circle on the input side. That means we first flip this value, then we fit into an AND gate or an OR gate. In reality, in chips, only one type of gate is used. They only use NAND gate. Okay, most likely in CMOS design, they only use NAND gate because NAND are small. It requires the least number of transistors. Then it's effective, is equivalent as using other type of gates by making some arrangement that you can use the only NAND gate to represent all the operations. Okay, so start with the buffer. Then how we can represent a circuit or a gate, we use a truth table. And for the in, if the in is 0, the output is 0. If the in is 1, and the output is 1. The NAND gate is special, right? So NAND gate works in this way. In 1, in 2, It's just an AND, then but flip the result. So why NAND gate is special? Remember this representation. So I was saying last Tuesday, I was saying leave this as an assignment. For a NAND gate, we actually simply need 4 transistors. Now for AND gate, how we can implement it is basically NAND gate and a NOT gate concatenated together. Okay, it's more complex. This is rather easy to implement. This is hard to implement. And if we only optimize NAND gate, it can really reduce the size. And if we consider other type of gates, then in fact, an AND gate is completed by a NAND gate and another NAND gate. So there's really no NOT gate in the circuit. There's only NAND and another NAND. Just combined in different way. So a NAND gate requires 4 transistors. Just be slightly aware that how many transistors it is required if we want to implement something. Okay, so let's say if we want to implement this logic, I don't want to read it. You can see this logic, how I would draw this circuit. Now, I just want to, on one thing, show you one quick way to draw a circuit that is always rather easy to understand, that I would simply put all the possible input on top. So just consider there are a lot of wires going on the ceiling. Then whenever I need some wire, I just drag one down. Okay, now I just put all the wires on top. Then say A and B first go through an OR gate. This is A or B, right? Then A and C prime goes to another OR gate. And these two are connected with an AND gate, and keep going on, right? This part is implemented in the same way. And eventually we OR these 2 parts, then we get this F. Okay, a rather complex implementation. But we don't want to implement in this way. We want to implement, we need to consider, do we really need this number of gates? Gates are not free. There are die sizes, and when they flip, they consume energy. So we want to reduce energy consumption, and we want to reduce gates. So we want to have the simplest form to represent this result. So by doing lots of calculation, eventually we can simplify it to A plus B plus D prime. Okay. Now we actually know C doesn't even matter here, right? So eventually we want to simplify into these forms. We can either simplify to sum of product or product of sum. Okay, that's the goal. So we can either do something like ABC plus BCD with prime somewhere, right? Or eventually we can represent in this form. And then the OR gate is, the AND gate is the last stage. That's the sum of product of sum. I will show you examples later. So, but eventually, if we implement this circuit in this way, we only need 2 gates, two OR gates, and then there's a NOT gate. Right? It's much simpler, saves a lot of die size, and the boss will be very happy. So, how we can simplify that? Then the best way to simplify a logic is to use truth table. Okay, I can tell you how it works. It's not really what if I have a truth table, is you want to have a truth table. And if you have a truth table, it's really easy to write the result out. Okay, so let's start with this XOR gate. Our goal is to use AND or NOT gate to represent the XOR gate. Okay, so simple example. This XOR, if they're different, our output is 1. If they're the same, our output is 0. So we want to generate a product of sum. That's the easiest way. You consider this one. We first look at the output. For output, we say here is a 1, right? Because eventually we want to have one. It's an OR operation. It's either this or this, right? It's either this or this. So we first need to get the representation of this one and get the representation of this one. So we only identify the rows where the output is 1. Then we look at the input. What will produce this one? This input will produce this one, but how this input can produce this one? We want to write an AND operation, so we want both sides to be 1, right? So 1 and 1 is 1. So how can we make it both sides 1? Is to flip this one. So if it's 0, we add a prime. If it's a 1, we just write it there. It takes some time to realize what's going on, but I can just tell you the rule, okay? And for this one, it's another example. 1, we just write x there, no prime. Y is 0, then we write a prime. And the other cases will generate 0, so in this case, there's a or. We don't care about those zeros. We just care about what cases that eventually it will generate 1. It's this case or this case, right? It's this case or this case. So we first write, how I can generate this case. Then this expression can generate this case. How we can generate this case, and this representation can generate this case. Okay. Later on, you probably need some more examples to feel comfortable about this. At the beginning, I really don't feel comfortable about this. But just see more examples, and then eventually we'll get comfortable. Okay, so this is pretty much very likely to be the simplified equation. Okay, write down truth table, identify once, then identify once, then write the product form of each one represents with proper prime sign symbols. Then we can say, okay, it's this one. Right. So if we implement an XOR gate with AND or NOT gate, this is how we implement it. Right. Other than the NOT gate, we need 2 AND gate. That means AND, AND, 2 AND operation. Then eventually OR these 2 numbers together. Okay. A more complex example, kernel map. Should I implement this kernel map? Okay. By the way, this may not be the simplest form. There can be more chance to make it simpler. So for example, this one, how we can, if we follow that way, we will write ABCD plus ABCD with some prime plus ABCD plus ABCD, right? We'll write those cases. We may even have more cases. But how we can simplify into this form? These days, these are pretty much implemented by computer. So we don't really calculate by hand. But kernel map is a way, it's an ancient way how we calculate, how we simplify this representation with visualization. So look at this one. It's a simple truth table. 3 input, 1 output. Now, how we can represent it? How we can represent in the product of sum, or sum of product method? Now we can simply write it as what's that? It's A prime, B prime, C prime plus A prime, B prime, C. And there's only 2 ones. And this is from the last slide. This is how we're going to implement it. Now, if we hand implement it, hand simplify it, yes, we can simply do this. A prime, B prime, C prime plus C. Then we know C prime plus C is 1, right? So then it's not important anymore. Then the result is A prime, B prime. So we know it can be simplified in this way. But can we guarantee that we can always simplify into the simplest form? And this is a kernel map. I find that pretty much if you only represent, use hand simplification, it's not terribly hard. You can just definitely do that with at most 4 symbols. So this is how we draw this kernel map. We first draw like 8 cells, then put C here and A and B here. So these are A0, B0, A0, B1, and so on. Remember, on adjacent cells, we consider it's only 1 bit to be different. Okay, so it's reversed here. Then we put down these ones, we fill in these ones here. So A0, B0, C0 maps to this cell, then we put 1 here. Then AB00, we put 1 here. Okay, then the rest is 0. So what do we do next? Next is we, remember in this form, this is what exactly I write on the whiteboard. Right? It represents just another way to write the product with sum format. In kernel map, what we do is we know when they're adjacent, there will be chances to take something out. Right? For example, these 2 cells, they have C prime and C to be adjacent to each other. So when it's adjacent, we circle them together. That's a single product. That's not 2 products. Okay. Then we represent each circle with a product. What's this product? It's basically by looking the value of A and B. And A and B are 0 and 0, so it's A prime and B prime. Okay. You don't know how hard I feel when I was undergraduate student learning these things. And this is something that I know that my professor will be part of the exam. It's the best type of question to take in an exam. It's hard, a little bit hard to remember, and it requires some skills. But I would say it's not very useful today because we always use computer programs to solve this problem. Okay, so the rule of circling is, first one, we draw a fewest circle as the fewest circle necessary to cover all the ones. We have to cover all the ones. Then all the squared in each circle must be contained once. That means we cannot put zeros there, right? Now each circle should span a rectangular block. That means we cannot do these 3 together. Right? It cannot turn. So we can only put these 4, but this here is a 0. So each circle should be as large as possible. So here, if this is a 1, then we should draw this as 1 circle, not 2 circles. Now, a circle may wrap around the edge of a K-map because these and these are connected. So we just consider it's a donut, right? So we connect them together. Because only 1 bit is changed, so there is a chance to reduce 1 parameter. A 1 in the K-map may be circled multiple times. It's okay. So in this way, how we circle them? We first circle this one as 1 circle, right? 1 square. And then there's an extra one. Now it should be drawn as large as possible. That's why we shouldn't really put it here, but we should draw in this way. But we cannot really wrap around because there are only 3. So it either 1, 2, or 4, or 8 of them in 1 circle. Okay, then eventually we want 1 circle to be 1 product form, right? In this way, then we look at what is changed and what is not changed within this circle. We'll only keep the thing that is not changed. In this case, A is 1 and 0, so A changed. B is 0 and 0, B didn't change, so we keep B prime here because B is 0. And C changed from 0 to 1, so we remove C. When you get lost, just come back here. C is changed, so we can remove C. Okay, it always maps to how we simplify this form by hand. Something changed, that means we can take the common parts out and remove C. Okay, then AC prime will be this part. I just want to let you know, okay, there exists such method. I won't put it in quiz. I don't think it's useful. I just want to let you know it's possible. Okay. Some simple form like this you probably need to know. You need to know. But kernel map, I won't put it in a quiz or test. Okay, an example. So probably you have played this 7-segment display decoder. So this is a device that we can represent a number there. There's a dot, so they actually use a byte, 8-bit, to feed in the control signal. You can see there are 10 pins in this case, right? And actually, there are 10 pins, and so there's a power and there's a ground. So that's why there's 10 pins, and each pin is controlling one. Each pin is controlling one segment. So if it's high, that means it's turned on. If it's low, then it's 0. That means it's turned off. But if we know the digit, we only need 4 digits to represent 10 digits, right? 3 digits can represent 8, 4 can represent 16. So we need 4 digits to represent 10 numbers. So this is a truth table that we can draw, right? You can see this is where it's A, B, C. This is 0, right? 0 only have G that is turned off, right? So that's how we generate this type of truth table. 4 input, and 8 and 7 output, right? So how we can design this type of combinational logic? And the rule is, do not consider others. When we design SA, segment A, we only consider SA. When we design SB, we only consider SB. Do not consider others. Consider the output bit by bit. Okay? So design logic for each output pin and consider each output pin as individual requirement. So let's look at SA. Right? The output is SA. And we put D0 and 1 there, D3 and 3 and 2 and 3 there. Then we put this kernel map like this. Fill in the kernel map. Okay. So for example, 0, 0, 0, 0 is 1, and we'll just put 1 there. Okay, then we circle them. Then we just write down the equation. This is the circuit that is required to generate this. Once we have this expression, we can draw the circuit that is required to implement this logic, right? The same way, then for some part, since there's others, right? So in this case, we just do not care those input. Then we can simply draw them as X. So if we draw them as X, so it can be either 0 or 1, we don't care. We can consider them as 1 if we want. In that case, then we can draw this circle even larger. If we can draw the larger the circle, the fewer the gates we have. Right? In this case, we have even simpler representation of the output. Okay, so at this stage, I think the takeaway is, if I know the input-output, we should be done with this lecture. So the takeaway at this stage is, if we know the output, input, if we can write down as a Boolean expression, or we can write down as a truth table, we can design a combinational logic that can achieve the result, right? So next lecture, we're going to talk about building blocks. So adders, now we start with this very simple logic. Then we're going to more complex operation. Here, some common building blocks there. Okay, and we'll talk about this in this next Tuesday.